In this video, we are going to discuss properties of ring homomorphisms. Let's discuss some properties of ring homomorphisms. So suppose you have a ring homomorphism. If R is a commutative ring, then its image turns out to be a commutative ring as well. The identity is zero element is sent to the zero element. If R has a multiplicative identity, and the image is non-zero, then the image also has a multiplicative identity. And if R is a field and the image is non-zero, then the image is also a field. Notice 4 is kind of best possible because I will point out there is a counterexample to what happens if you replace the word field with integral domain. It is possible for R to be an integral domain and phi of R is not. So you can combine 1 and 3, but you can't add the word 0 divisors and still hope that the conclusion works, unfortunately. And by that, I don't mean just this silly example. I mean something more complicated. Most of this theorem is taken from the textbook, although if I remember correctly, I decided to make these slightly more general statements. However, first we're going to prove a different statement that technically should have been proven and stated first, because it's actually implicit in a lot of the other ones. It's that the image of the homomorphism is a subring. That technically needs a proof. And it gets used a lot in later results in the book, so we do need to show it. So how do we need to prove it? Well, first off, certainly note that the image is non-empty, because, well, there's at least one element in your ring, R, and so phi of 0 is in the image. So there's something there. All right, now let's take two elements, x and y, in your image. Then x has to be equal to phi of R for some R and S, and y has to be equal to phi of S for some R and S in R. This is the definition of image. Now, what do we need to show in order to be a subring? Well, we need it to be non-empty. We need closure under products. We need closure under differences. So let's look at product. X times y is equal to phi of R times phi of S. Phi is a ring homomorphism, so that's just equal to phi of R times S, which is in phi of R. So we're closed under multiplication. Oddly enough, it turns out subtraction is a little more complicated. There was an alternative way to do it. An alternative way would be to show you're closed under negation and addition separately, which is actually a little easier, but here's the underhanded trick to get them both at once. X minus y is equal to phi of R minus phi of S. I want to be able to use the additive ring homomorphism property. I can't do that with subtraction, unfortunately, but what I can do is I can introduce a minus s plus s in the first term so that I can apply the additive ring homomorphism to get plus phi of s here, so I can cancel out the phi of s's. So that's what I do. And so if you do that, then you see that x minus y is equal to phi of R minus S. So x minus y is in the image. This also does show you that, in fact, phi of R minus S is equal to phi of R minus phi of S. So by the subring criterion, phi of R is a subring of S. All right, now we can get to our other types of results. If R is commutative, then so is the image. So now we know it's actually a subring. We want to show it's a commutative subring. So let's let x and y be in the image. We'll say x is phi of A and y is phi of B for A and B and R. Why A and B? Because, well, why not change it up a little bit? X times y is equal to phi of A times phi of B. So phi is multiplicative. That's equal to phi of A times B. Since R is commutative, AB is equal to BA. Since phi is multiplicative, phi of BA is equal to phi of B times phi of A. It's equal to y times x. Congratulations, we took two arbitrary elements in the image. We showed x times y is equal to y times x. So the image is commutative. All right, the next property, your ring homomorphism has to send 0 to 0. Well, this is one of those lovely results that follows from saying, well, if you have a ring homomorphism, then it's an additive group homomorphism. You're going to hear me say this quite a bit. I don't know if the textbook goes that approach. You don't have to do that approach. You can do things the hard way, but this shortcut saves you some effort because it allows you to say, well, we already proved this result. That is, if you notice phi of x plus y is equal to phi of x plus phi of y, and R and S are abelian groups with respect to addition. And so phi is a group homomorphism with respect to addition. And we already had this property earlier in the course, that if you have a group homomorphism, then it sends the identity to the identity. And in an additive group, 0 is how we denote the identity element. So 0 sent to 0. And yes, I will do this an awful lot to save ourselves some work by just pointing out we already did this for additive groups. So therefore, this additive part already holds for the ring homomorphism. That way we only have to focus on multiplication. Now suppose you have a ring with a multiplicative unit. If your image has got more than 0 in it, then phi of r is also a ring with unity. Why do I need this bit? Because it's usually customary to insist that the unit is not 0 itself. And so if you end up with the 0 ring, we usually say that the 0 ring does not have a unit. So you have to make sure you get something else. Because I forgot to mention it, but you could always create a ring homomorphism between any two rings by sending everything to 0, which is kind of a useless ring homomorphism, but it works. What is this unit? Well, you would probably guess it should be the image of 1. And if you guessed that, you'd be right. So let's prove it. Let's let 1 be the image of 1. Let x be in phi of r. X is equal to phi of r for some r. Well, let's do the multiplication. 1 is phi of 1, x is phi of r. Phi is a ring homomorphism. 1 times r is r. Phi of r is x. Congratulations, we did it. Okay, we did half the work. I'm not assuming r is commutative here, so we have to do the other half too, but it's the same proof backwards. So x times 1 is phi of r times phi of 1, phi of r times 1 is x. Although I probably should have put x here. So phi of 1 is the unit. So far we've gotten a lot of the properties. Here's the fourth one. If R is a field and the image is non-zero, then the image is at a field itself. Well, what do we need to do? We need to show that the non-zero elements in the image form an abelian group for multiplication. That's the definition of a field. Well, that's not the whole definition. The other part of the definition is that phi of r is a commutative ring. Or, I mean, is a ring. But we already had that part. That was part 0. So what do we need? We need associativity. Well, we already know phi of r is a ring, so multiplication is already associative. We need commutativity. Well, we already showed that. That was part 1 in this video. The first thing, that the image of a commutative ring is commutative. And R is a commutative ring since it's a field. We need a multiplicative identity, but that was the thing we just got done showing. R has a multiplicative identity, so phi of r does too. So the only thing we need left is to show that phi of r has inverses. So let's let phi of r be a non-zero element here in the image. let's just multiply phi of r by phi of r inverse and see what happens. Well, by ring homomorphism properties, it's phi of r inverse times r. It's phi of 1. As we just saw, phi of 1 is the multiplicative identity for the image. So what did we just show? We showed that phi of r has an inverse, and its inverse is phi of r inverse. So this is just like the property for group homomorphisms. The inverse gets sent to the inverse. Only we didn't state it that way because notice the difference between group homomorphisms here is we weren't assuming in advance that the image is a field. We weren't assuming in advance that inverses existed. So here we managed to prove inverses existed, and we managed to prove this formula for them. Note the fact that R is a field is assumed right here. You need R to be a field to guarantee that R has a multiplicative, this element has a multiplicative inverse in the first place. Finally, it's always an interesting thought to ask ourselves, well, what happens if R is an integral domain? Is it possible that phi of R is not? The simplest example is this one. So we already did the maps from Z to Z mod NZ. We'll pick n equals 4. We already know this is a ring homomorphism. Z is an integral domain. Z mod 4Z is not because, well, 2 times 2 is 0, but 2 is not.